Okay, so let's start the last session of this workshop. So the next speaker is Andrini, and he's going to tell us about understanding ADS-CFT 3, ADS-CFT2, success and challenges.
Okay, thank you very much for the invitation. It's my first time in Athens, and I really enjoyed. And I think, like everybody, I really look forward to taking advantage of the beautiful day outside. So I'll try to be brief, and I like to thank everybody that came back after lunch for the endorsement of like being in here instead of out there, enjoying the day. So exactly this. This is a scientific talk. After this, I will also give you a brief presentation about cost for people that are interested. And after that presentation, I will do the cost reimbursement if you are an invited speaker paid by cost. So this is just for in this situation and are interested, they can stay a bit longer afterwards. But for everybody, let's just jump right in, and I'm going to tell you something about ADS-CFT2. A lot of activity in the last years, and I've been working on this since my PhD, so now it's sort of a personal challenge to me to see this through somehow. And there have been many successes, but also many challenges, many things that we thought were not quite right. So I'm trying to demystify what was done. And since it's the last talk, and we are all, like in a very convivial atmosphere at any moment, let's try to keep this thing interesting for everybody and keep it very informal. So at any point, please don't hesitate. So I will focus on backgrounds and the maximally supersymmetric ADS3 backgrounds. They are of the type ADS3 cross S3 cross something. And they come in different families. You can have T4, that's the simplest case. You can have a K3 instead of T4. Or you can have, and that's a bit complicated, two spheres, so S3 cross S3 cross S1. And that's because, as Fiona was saying, you can change a little bit the spheres. And all of these backgrounds, with all these freedom and parameters, they have 16 real killing spinors. So the 16 real supersymmetries, half of ADS5. And all of them should be dual to n equal 4 conformal field theories in D equal 2. And broadly speaking, it's unknown what the dual theories are. And what I mean by this. For the purpose of this talk, and also for the purpose of what people have been doing, I focus on ADS3 cross S3 cross T4, which is the backgrounds. And to cheat even a bit more, very often I will T4 as if it were R4, meaning that I will not really look at winding the torus or other similar effects. The thing that one needs to realize is that this is a family of backgrounds because there are many moduli. One obvious modulus is the overall size of the space with respect to the string length, like in ADS5, for instance. So it would be like string length over the radius of ADS. The radius of S3 is the same as of the radius of ADS. But there are also more parameters in this case. Before going into that, let me just describe a little bit the space. So probably these are things that are familiar to most of you. So ADS3, that's of 2,2. And it's very convenient to treat it as two copies of SL2R. I indicate these two copies as L for the SL2 generators, or L for a left and right copy. So this would be the left and right SL2s of the dual conformal theory. Similar for SU2. Sorry, for SO4, you have SU2 plus SU2, and again it's J and J with Greek indices for the SU2. And then what we are after, the simplest observable, is the energy spectrum of string states. So this is the spectrum of L0 plus tilde, which are the non-compact Cartans of SL2. In practice, what I will often consider instead of L plus L0 tilde is the light cone energy. So that's E minus J, the total energy minus the total R charge of the state. This is a natural quantity, has lots of nice properties, so I will often refer to this instead of 0 minus L0 plus L0 tilde. And it doesn't really matter because, of course, the difference is charge, which is quantized, and it's easy to find. So far, so good? Okay. Let me start from the of ADS3 backgrounds And these are pure NS backgrounds, which you can study very easily, or rather easily, in the RNS formalism. And this was done almost 20 years. And the idea is that you start from NS5 branes, K of them, and a very large number of fundamental strings. I'm doing perturbative string theory here, so the string will be small. I'm interested in the planar spectrum if you want. And then you get a metric, which is the metric of ADS3 cross S3. And you get a B field such that dB is the volume form on ADS3 and on S3. This is written in some notation where the radius of ADS and the radius of the sphere is 1. So I raise the string length and reabsorb it so that everything is dimensionless. And then you only have one parameter, because essentially you are dealing with a Wessel-Minowitten model for SL2R and for SU2. And the only parameter that you have, which is quantized, is K1, 2, 3, 4, which is precisely the number of NS5 branes. So it becomes of some Wessel-Minowitten model with a non-compact part and the compact part. More specifically, a supersymmetric Wessel-Minowitten model on the worksheet in the RNS. And the tension of the strings in these units where everything is scaled to is just K over 2 pi. And indeed, because in the RNS formula this is a Wessel-Minowitten model, you can solve this theory. And I'm going to show you briefly how this qualitatively. So the idea is that, first of all, you have to decouple the worksheet fermions. And this gives you some shifts of the level of the SL2 and the SU2 level by 2. And because of this shift of K minus 2, on the SU2, you see that everything is fine if K is 2. It's also kind of fine if K is 2 because you have level 0. But this is not kosher if K is 1, because then you have level minus 1. And that's a bit fishy or non-unitary. Now that for K equals to 1, you have to do a different approach. But let's deal with the general case. And what you say is that you have a bunch of modes of the Kac-Moody currents for SL2 level K plus 2, SU2 level K minus 2. You also have the T4, so you just have 3 modes on the T4. And you pick some reference, highest weight state for the SL2, SU2 Kac-Moody, and you act with a bunch of creation operators in the left. And then Virasoro constraint. The Virasoro generator is constructed Vara construction, so it's a quadratic object in terms of the currents of the Kac-Moody. And you get a condition that something square has to be equal to 0. And you solve it for L0, where L0 the weight of the SL2 representation, which is a continuous parameter, so it's a function of such an equation. Whereas J0 is quantized because SU2 has quantized representations. So this is not the story. People that know the whole story know that there are long strings, there are spectrally flawed representation. That's true and it's important. But the point that I want to make is that this is a very simple spectrum. If you have worked, for instance, in ADS5 or in N equal 4 sub-3 and you have computed or seen the dimension of Konishi at 1 loop, 2 loops, 3 loops, it's very complicated. Here is the formula acting kappa. So in principle, this thing is something that you should expand in 1 over K, which is the tension. But I can just complete formula, closed formula in K. Very simple and also very degenerate. Because if I have a state which is created by acting with excitation with a total excitation number N1 plus N2 plus N3 very large, then I can realize a state with such an energy in many different ways, and these are all degeneracies of the spectrum. So these features, they are not typical of ADS3 CFT2. They are typical of these Wessel-Minowitten grounds which sit at very special points. But there are more general backgrounds, and as soon as you consider the more general backgrounds, things become much more generic, much more, and of course, much more interesting. So this was the first point that I wanted to make. All good so far? Well, this I already said. The generate doesn't depend on the individual NJs. Then there are mixed fluxes, which also have Ramon-Ramon background fluxes. And the way that you can think of generating is that you start from your NS background with some K, and you can turn on some modulus in this system of fundamental string and NS5 brains. This is explained in several papers, including this one, where it's very clear what this modulus does. And at the end of the day, in the, say, Grange-Schwartz action, you get that the amount of B field, or the amount of H, is a little bit lower. It comes with a parameter which is Q, between 0 and 1. And then you turn some F3, which basically is such that the coefficient in front of the H and of F3, they square. If you square them, they give you 1. So you can sort of rotate between these NS Ramon-Ramon fluxes. And for any value of these two, you have a perfectly well-defined supersymmetric background with 16 killing spinors that has no problem. Okay. Some of you might actually know that this is related to S-duality or more generality of the background, but I don't like to think in terms of the dualities because I'm looking at the spectrum of the planar string theory. So these dualities, they typically change the string coupling, so they take me away from this planar limit. So what I think is that I'm in the planar limit and I change the background. So it's actually a little bit convenient to re-express the parameters of the theory in terms of K, which is this nice quantized parameter. Is the one that would sit in front of a Vesumino if you write the action. That's why it's quantized. And K is related to the tension through this parameter Q. And produce another parameter H, which is related to the amount of Ramon-Ramon flux. So that the tension is sourced by a combination of H and K, square plus K square over 4 pi square. So this is my generic background. And what is observed is that indeed, when you turn on this Ramon-Ramon flux, all these degeneracies lift, the spectrum becomes much more complicated. But of course, this background with Ramon-Ramon flux is very difficult to study it in the RNS formalism. People have tried, but it's very, very cumbersome. Moreover, there is another background where you don't have any K at all, where you just have Ramon-Ramon flux and no NS flux at all. This you would obtain by straight starting from the 1D5 brains. And that's very, very study in the RNS formalism because you cannot even perturb around some nice NS background. So the question is how to study them, and if you know me, the answer will be integrability. And the idea is that given the success for ADS5, cross S5, and ADS4 cross CP3, which are all Ramon-Ramon backgrounds, you can hope to do something similar. Why you can hope to do something similar is that these backgrounds with this parameter Q, with the parameters K and H, which are arbitrary, are classically proven by Cagnazzo and Zarembo. And then you can try to study the theory in light cone gauge in the way that in ADS5 gave you the integrable structure. Now, to ADS5, the integrable structure came in large part from N=4 superior Mills. Unfortunately, here we don't have such a nice theory to study. So we are a bit constrained to study things on the string side of things, which makes things a little bit, if we had very good control on both sides of the dualities, like people had 5 and N=4, then life would be substantially simpler. More on the dual theories later. Okay, so the aim of the game is to find the spectrum for any K and H, and I'm going to basically tell you how it's done briefly, and then I'm going to tell you what are the results. So one important part of the trick is that we go to light cone gauge, to some specific light cone gauge, where we pick a light cone X plus, we fix the conjugate momentum P minus to P constant density. And then one immediate upshot is that the Hamiltonian on the worksheet, which is the thing which is to time on the worksheet for this two-dimensional theory, is also equal to H dot, which is the target space combination of charges that I told you I like. It's L minus J. So the spectrum of the string gets mapped to the spectrum of a two-dimensional model, which is exactly what I would like. And again, like everything, this H, this total Hamiltonian, is a component that comes from the chiral part and the anti-chiral part with tildes and tildes. Another thing that happens is the size of the worksheet is fixed. You don't have a parameterization invariant gauge fixing in terms of the total R charge. Now you try to find out what is the symmetry algebra of this theory. Before the gauge fixing, you had PSU1,1/2. So this is which in SL it has an SL, sorry, an SU1 which is SL2R and an SU2, and it comes in two copies, one with tildes, one without tildes. This PSU1,1/2 has a BPS bound, and the BPS bound tells you precisely that L minus J is greater or equal than 0. So that's also why this quantity is very nice. It is the quantity that's bound, and using it for our gauge fixing guarantees that Hamiltonian is greater or equal than 0, which is something that we want. And because this BPS bound preserves alpha of the supercharges, presentation preserves alpha of the supercharges, this gauge fixing preserves some supersymmetry too, which is also nice. The killing spinors in the full algebra, PSU1,1/2, are, well, 2 copies. There are 8 per copies, and I call them G alpha AM. M is the SL2 quantum number, is SU2, and the A is just something that tells you that there are more charges that you want. There are 2 families, A equals 1 and 2. When we fix the light cone gauge, because the gauge fixing is alpha EPS, it's precisely alpha of the supersymmetries to survive. And if you think the ones that survive, they have to commute with L minus J. But if they raise L, they should raise J, and if they decrease L, they should decrease. So that's how it goes simply. And indeed, these are supercharges that survive. This notation is the one that is useful if then you want to go to the CFT2 dual, by the way. It's very standard in CFT2 notation. And you look what algebra they obey. There is a part of the algebra which is very simple. Essentially, a G plus with a G minus, it gives you L minus J, and same thing with a tilde. Statement that if you have a supersymmetry generator and a supernormal generator, their anticommutator will give you station of R symmetry and energy. In the right, everything is factorized. And that's something which is very surprising if you have not studied the ADS5 integrability story, and it's not surprising otherwise, is that this algebra gets an extension. So now you get a commutator between left and right supercharges, so the ones without the tilde and the one with the tilde, which is something new. Is this C plus and minus minus. And you see this C++, it R charge and it carries some SL2 charge, and in the right, minus minus, same thing. And it couples supersymmetry algebras that were completely factorized before. This is something that happens also in ADS5, in ADS4. It's noticed by Beisert in the context of n equal 4 super. And the tricky part of this algebra is that it's an extension that you have after the gauge fixing, but is not there in the full algebra when you consider physical state of the full algebra. The full algebra is factor 4. So somehow this extension should be such that it disappears when I consider physical states of the full algebra. Indeed, so these are central extensions. To drop all pluses and minus, I just call them CNC dagger. They are conjugate to each other. And the way to understand how it works, that you have these new central charges, is to do some classical computation to try to understand what they look like. And you can do that. And what you find is that, first of all, extension is proportional to h, which was the parameter related to the flux. So the central extension is not there if you study just the Vesumy-Witten case. Second, for a state on the worksheet of the strings created by a bunch of excitation of momentum P1, Pn, or if you want of mode number N1 up to Nn, the central extension takes, it is a function of the total momentum of the state. And like any good string in light-cone gauge, you find that there is a condition on the worksheet momentum of a state, meaning that it has to be 0 mod 2 pi if the state is physical. So if the state is physical, then actually this central extension annihilates the state and everything. You might wonder, I mean, if it's there but then it's not there, going on and on about the central extension. Well, it turns out that to compute the integrable, to find the integrable structure of this model, you have to consider first non-physical states. So it's very important to have this algebra with this extension, and only at the very end of everything you can say that the states are physical. So even if in the end for physical state is not there, because the integrability structure knows about the intermediate steps, I need really to be careful and keep this in mind that I have this central extension. Then you can study the representation theory of this centrally extended algebra, and you find that these excitations are the A dagger, which are basically the modes of the fields of the string. So in the of your A transverse bosons and fermions, yes?
Does the central extension have like a homology, like a BRST type of?
Not. I don't think about it in that way. So yeah, I cannot comment too intelligently on that. More questions? Just disappointing answers in the future. Yeah, I just wanted to say that you can find that these A daggers, which are the modes of the string, they transform in some spatial representations of the string in short representations. That's just because short representations are small, and otherwise you wouldn't be able to fit all the particles in the right way. That means that the representation solve this constraint. H tilde is equal to CNC dagger. H and H tilde were related to the total Hamiltonian. You can invert this constraint to find what the total Hamiltonian is in terms of the moment H and P. And if you know what the total Hamiltonian, you know roughly the energy of a state, because you just stuck with the total Hamiltonian on the state. And the form of this dispersion relation, which you find by representation theory, is pretty messy. Is this thing here. So let me. There is a piece which is a square under the square root. It depends on 2 pi times the momentum. K was the NS flux, or the level of the Vesumy-Witten model. There is a parameter mu. Mu just has different representations. In fact, it turns out that mu can be 0, 1, minus 1. And then there is a part on the Ramon-Ramon flux, which is periodic. It's related to the fact that we add e to the IP as the form of a sine square. So in particular, if I take h equal to 0, the dispersion becomes linear. And that fits very well with the fact that the total energy depended only on the sum of the mode numbers in the Witten model. If I take k equal to 0, I get something like this, which is a lattice dispersion in a sense, and it's also very similar to what you have in ADS5. In general, I have something in between. You immediately see that if I have such a dispersion, due to the energy of a multi-particle state, it will not depend on the sum of the momenta, on the total momentum, but it will depend on the individual momenta. So there won't be as much the general case where the dispersion is linear. Okay, so far? All right. Then what I do is that I want to fix on this worksheet of the string where I have my excitations. No. The honest answer is no. We don't know it. I'll comment more about it later. More questions? Okay. So I take my string. I have excitations, which I can think of as part of this dispersion with this energy. And if the force of the string big is a plane, I can consider the scattering theory on this plane. And then whatever it is basically an intertwiner of the two particle state. I send two particles in and I get two particles out. Well, why don't I get more particles out? That's the magic of integrability. In general, you would get n particles out, but this is an integrable theory. Turns out that you only get two particles out. And this S matrix is something that you can try to fix, compute perturbatively. Ideally, you do both, and then you compare. And the matrix part of the S matrix is very easy to fix because it's fixed by this representation theory. The prefactor is not fixed by a bunch of linear equations. Unitarity, crossing symmetry, analyticity is harder. Once you know that, very schematically, so here I'm cheating a little bit, very schematically you say, well, the worksheet of the string was not really a plane, but it was a cylinder of size the R symmetry. In my gauge fixing, the size of the cylinder was the R charge of the state. So I better say that I have some quantization condition of the type e to the I size of the worksheet is equal to 1. This has to be corrected a little bit by phase delays that are, or phase shifts due to the factor tethering. This is a standard set of equations that goes under the name of Bethe ansatz, very famous. And what you find is that you solve this equation for the momenta. You find that at leading order, you get something for free that looks like theory, 2 pi a number divided by L, plus correction due to the fractions in the S matrix. And it's a set of algebraic equations. Maybe you can analytically, maybe you can solve them numerically, but you can solve them. And the result, you stick it into the formula for the dispersion total energy. This is not the entire story, because the topic of wrapping corrections, like Charlotte was mentioning, I don't want to go too much into detail, but there are additional complications due to the fact that you have true finite size effects, basically virtual particles that travel across this cylinder. And there is ability to treat them is just much more complicated than this cartoon. But in principle, is a way. It goes under the name of thermodynamic Bethe ansatz, or mirror thermodynamic Bethe ansatz, or quantum spectral curve. So the results of all this story is that, first of all, you can do integrability for the case which we know very well, which is the Vesuminov-Witten model, the NSNS. And you find, again, expected from the RNS formalism. So that's a nice confirmation. Then you can take the case which is opposite, is the one related to the one only Ramond-Ramond flux, very similar to ADS5 in a way, and the spectrum, and you get a new model which is different from anything that we have seen. Very interesting. And then you can try to do the most general case, and that's what is progress right now. Basically, for this last case, we are at the point where we are finishing to fix the S matrix and this dressing factor, which is the hardest part to fix. There is a bit of a puzzle here for the K0 case, for the Ramond-Ramond. Actually, this calculation was done independently in two different. One was done by my collaborators and myself, along the explained. you look at the symmetries, you look at the S matrix, you look at the Bethe answers, the corrections, you get these equations which contain everything. The other was shortcut, where you say, well, there is this quantum spectral curve machinery for ADS5 and for ADS4. Maybe we can conjecture it for ADS3 without any of the intermediate steps, without deriving it from this intermediate set of considerations. And the natural question whether they agree or whether some changes are needed in one or the other, and that we are looking at in order to reconcile them and see if maybe one indicates that the other needs to be corrected somewhat. So this is also work in progress really in these days. Then it is different from ADS5. It's still different from ADS5. They are similar, but they have important differences. So the two important differences between this theory and ADS5 is that there is a natural split between chiral and antichiral symmetries and rotations. First, and second, there are particles that are massless. I glossed over a little bit, but when I add this mass, mu equals 0 is an allowed value, and for mu equals 0, omega is 0. The energy is 0. So they don't have a mass gap. That's a feature, not a bug. People that have worked in ADS3 know that there is a complicated structure for the protected state of the theory. It's rich in ADS5. It comes from the Hodge diamond of T4. And these massless excitation, and in particular the massless fermions, are needed in order to reproduce these BPS states in the Green-Schwarz formalism. In the RNS, they appear in a different way, of course. More questions? Okay. Then I would like to comment on, and that's related to the spin chain picture and the dual CFT picture questions. I want to comment a bit on what happens when the tension is small. When the tension is small, the string theory should become difficult, but some dual conformal becomes simple. Think of weakly coupled N=4 superior Mills. And that's also where the spin chain picture is simple in N=4 superior Mills, when the coupling is small. And it turns out that there are two ways of considering small tension. Well, the smallest tension that you could have is to say that K is 0 and H is tiny. H is continuous. So it's 0, H is tiny, the tension is very small. And that's related to the D1, D5 system of branes at small tension. But the near horizon limit of the D1, D5 system has small tension. You have K equal to 1, which of course has been studied a lot. This is referred to as the tensionless limit. And then you take K equal to 1 and H very small, maybe even 0. And that's what gives you the symmetric product orbifold CFT. But it has, strictly speaking, a little bit more tension. And then, of course, you could have K equals to 2 and H small, but at some point, you know, you're just at some generic spots. It seems like that K equals 0 and K equal to 1 are maybe the most special ones. So let me start from K equal to 1, which is the most famous and best studied, because the dual CFT is quite nice. It's complications as well. And the idea is that this is the symmetric product orbifold of T4. You take a supersymmetric bosons on a torus. You take n copies and mod out by the action of the symmetric group Sn. And then you take n to infinity to take the large n as in holography. The states are labeled by the conjugacy classes of Sn. That means that you should look at your Fock space in terms of cycles, single cycle, multi-cycle, etc., like you do for traces in N=4 superior Mills. And if n is very large, there is a section like in N=4. You can consider single cycle states. Much like in N=4, you can consider single trace. And everything comes when you know cycle once. So single cycle means you have your bosons, your fermions, you have a cycle of length L, and under these, basically, you just have ZL. Right? you have L copies of your CFT, and the boundary conditions such that from the first copy you go to the second, from the second to the third, and from the L to the first. And all the other N copies are basically trivial. And because you have these many copies, what you get is that the mode numbers are not only quantized not in integers, but in 1 over L. Essentially, you can think of gluing in some covering space all these L copies, and now you have 2 pi L size of your cycle. And still, you need a physical state condition, which is the state under the orbifold, and that just tells you that the sum of the members of the chiral part minus the sum of the antichiral part should modulo L. So there are, again, twisted sectors is L or a multiple of L, but you have one condition, which is, of course, very much reminiscent of the level matching condition. That's basically what it becomes in string theory. And the spectrum is free and super degenerate. Right? Just the oscillators, they are just quantized in 1 over L instead of being quantized normally. An overall condition that the total n minus n tilde should be 0 mod L. And the energy, meaning L minus J, so now I'm in the CFT, L0 becomes the SL2 cartan, J is the SU2 cartan of their symmetry. I can compute minus J, I can compute what H dot is, and it is n over L, plus n tilde over L. And you can see immediately that this is reproduced by the complicated dispersion that I had before. L root, if first I put H equal to 0, because I don't have any more amount, so I don't have that sign, then I have just an absolute value of something, and I put equal to 1, and I just get this very simple energy. And with this simple dispersion relation, you see the thing that I have to say is that the momenta are quantized as 2 pi u over L, as if this thing is a free theory, which basically it is. So in a sense, there is a very trivial spin chain interpretation for this symmetric orbifold. It's theory, and you just say, well, the L cycle sector is an L cycle spin chain of free particles, which is true, but doesn't really buy you all that much because the theory is just so simple. You can write the function very easily. What is more interesting is how you turn on the deformation, because to turn on the deformation, we want the supercurrents left and right not to commute anymore. And that looks fishy, of course, in conformal field theory, but if you stop and think about it, it is strange in this case. So the point is that there is a deformation of this symmetric orbifold. There are several, but in particular one which sits in the two-cycle sector. You have to pick a particular state of the two-cycle sector with some supercharges, and you construct an operator which is marginal and this new charge, and then you can deform the theory by means of this operator. And what you would expect is that in the deformed theory, in the presence of this operator, you can have it which is constructed out of chiral excitations, but is not anti-chiral, guys. There are a couple of problems with this idea. First of all, you see everything is quantized in terms of n over L on the one side. On the right, actually, I'm on a vacuum which is not L, but a size L plus 1. That turns out to be true for two reasons. For people that know integrability, is because the central charges, or this central extension, has to do with Lensing effects, like in the Beiser story. For no CFT or group theory, is because if you have an L cycle and you want a non-trivial OP with a 2-cycle, you get an L cycle, because you have to glue them with a common site. So that's basically why you get this shift. You cannot have a non-trivial OP between an L cycle, a 2-cycle, and another L cycle. The right-hand side has to be quantized in n over L plus 1. And that's a problem, because then the energy that you have on the left, which is 1/2 plus n over L, well, should be equal to whatever is on the right, which is minus 1/2 plus n over L plus 1. And then you also have the shift due to the R charge. The point is that you have to match something that is quantized in units of n over L and n over L. That's not great. So how do you do it? By the way, just to say, the total energy from the vacuum, it also carries some energy. That's why here you have minus 1/2 and here you have plus 1/2. It's because this guy carries R charge in the left and in the right, and dimension in the left and in the right. Technical point, if you want, we can discuss. The whole point is that to make sense of this, you have to take some limit, and you should say L is equal to infinity, n is equal to infinity, and E over L is fixed. That's like when I was doing my S matrix was defined on the plane. So L, the size of it had to be, strictly speaking, infinite to define the S matrix. So it's not so strange, and it's also similar to ADS5. So the thing that you want to compute at this point is something like this. This coefficient, which is what the action of a right guy on a left excitation is, this coefficient should appear in some correlation function, where here you have your left excitation, here you have the right supercharge, here you have whatever you get on the right hand side, and you insert the deformation operator. So this is something that you can try to compute, and people have done it. Actually, this was done a very long time ago by a guy. They did it with some approximation, including the fact that they took n over L to be small. They were interested in some sort of PP wave limit. And one confusion is that they were trying to match with the Ramon-Ramon case, which is the right place. We know that it should be matched with k equal 1. Very recently, this was done by Gaberdiel, Gopakumar, and Nairtz. So this was for n over L fixed, and it was matched with k equal 1. They met how you identify the representations with respect to the string, which modes correspond to the torus, which modes correspond to what else. And with Sergei Frolov, we very shortly, the day after their paper, we explained how to fix that part. And we basically checked that this would reproduce the same S matrix as was done in integrability, which sort of is obvious from representation theory at that point. But one thing which, in the rush to put out this paper, we didn't immediately realize that there is actually a puzzle or a problem with this computation, because the issue is this central extension is only there if you go up. You needed the total momentum to be non-zero. Otherwise, and the same is true here. Basically, is this observation that is equivalent when you compute the correlation function is closely related to being on shell and being physical. And this part they didn't quite do, so they basically cheated a bit. And the result makes sense, is the same as in one, but it's not clear whether you can fix this computation in a way to something more than what was already known from integrability. So that's a bit of a problem that is important to resolve. Yes, the central extension is related to this deformation. Remember, the central extension was proportional to the Ramon-Ramon flux, and the deformation parameter has to be related in some way to the Ramon-Ramon flux, and this is basically the relation. Same thing at first order. Of course, if you were super smart, you might have a complicated function when you go higher and higher. Yeah, so when you are in the undeformed theory, everything is completely split between left and right, and it is the deformation that brings it together and gives this action. More questions? Okay. Then I wanted to tell you about this other tensionless limit, which is k equal to 0 and h very small. And then you look at this dispersion. This is the k equal to 0 dispersion relation. Mu was the mode, the the label of the representation is basically the mass of some particle on the worksheet. And you see that the leading order corrections, the leading order contribution to the energy comes to the mu equal to 0 terms. Mu equal to 1, 2, 3, and so on. At small h go like 1 over h squared. And the to 0 terms, they go like h. So they come in quite a little bit earlier. So what we wanted to do, to look at this sector of the spectrum, it turns out that the h equal to 0 terms are the modes in ADS3 cross S3 cross T4 that come from the T4 part of the spectrum. That sort of makes sense because the T4 modes are in translation, so they cannot be a mass when you write a Lagrangian for a sigma model on T4. So these are the massless modes of this theory, and using the whole integral machinery, accounting for all this wrapping, what we wanted to do is to say what weak tension dynamics or the weak tension spectrum of these modes. Maybe you think, well, okay, maybe it's again the symmetry product for T4. Maybe, you know, like it looks different, but it's the same theory again. So what we did is to take this complicated set of equations of the TBA, expand it in small h, and naively we would expect if the theory was just a simple free theory, it should look like something like of some integer, the mode number over L plus corrections. And this is some computation that we can only do numerically. Here are plots for some simple states. Some length for this state, so this is the total arc charge of the state. Here is 4 and 16. In paper there are many other examples. And what you see is that with respect to the dashed line, which would be a free theory with this sign dispersion, something which is different because there are interactions. So this dot shifted with respect to the dashed line, but close enough to the dashed line. In particular, as L becomes larger, these wrapping corrections are small. The energy is similar to that one of a theory of particles with dispersion relation sine p over 2, however interacting. So there is another plot that I didn't put here. If you have a multi-particle state, the energy of the multi-particle state is different from the sum of the energy of the individual particles. So there is really some interaction going on. Okay. To conclude, of the art is that you have this big landscape of ADS3, ADS2 backgrounds. I've only talked about T4. You could ask all these questions of K3S1 as well. There is a simple coorder. These are pure NSNS, and you can study them on the worksheet in the RNS formalism and all that you want. You can also do integrability, of course, but it's much nicer to do that. The spectrum is simple, it's very degenerate. And then when you turn on this mixed flux, this Ramon-Ramon flux, you go to the mixed flux case, and the spectrum becomes non-degenerate. It becomes much more. And this is the case that you can only do by integrability. This general case of mixed flux is the one that we have not finished doing. We have done with the extreme opposite of an SNS, which is just Ramon-Ramon. This is when you don't have any B field. Is the one related to D1, D5. And we have these equations, this TBA equation and this quantum spectral curve, and both from our group, from the TBA, we have these predictions from this tension, and for the quantum spectral curve, they have other vectors of the theory. So far, because the techniques are a bit different, we don't have overlapping predictions. It takes quite a bit of work to get out the numerics and do it carefully. But this is more or less solved, and the next mixed flux case will also be solved, hopefully. This is all, of course, very nice, but the real question will be to, for instance, understand what's the dual in the pure Ramon-Ramon, so the weak bit of the D1, D5 system. We know what the spectrum is, but I cannot give you a microscopic Hamiltonian or a spin chain like in N=4. So that would be very interesting. And of course, have complete control when you start from the RNS string or to the NSNS setup, and you start turning on this Ramon flux and completely follow what it does. That would be, of course, very interesting, even just to understand better how to Ramon flux in string theory from the worksheet point of view. Okay, I think that's all I wanted to say. Yeah. Yeah. Yes, and try to explain. Let me try to go back to this dispersion. Right. So the dispersion relation is just linear. In this case, it has this simple form, and it is the same in all particles. The S matrix becomes proportional to the identity in this case, and then it's very similar to what Dubowski did for the flat string. The only difference is that here you have this mu to something called spectral flow on the RNS side, which the whole story there. But up to this thing is very similar to doing the TBA for the flat string in 10 dimensions. So it's a similar story. You mean a Q deformation? Yes. For Q deformations, yes. And it's rich in this case because you have two copies, left and right, of the algebra, so you can Q both of them independently. You can also do TSTs and so on. So TST is relatively simple because it's just boundary condition. Deformation is relatively simple for the matrix part of the S matrix, but the vector is trickier. It's going to change, and we don't know. In principle, though, I think it should be possible. Certainly the case in which you Q deform in the same way, which is more physical also in the dual. I mean, it's an interesting question. To my mind, it's more urgent to put under complete control the undeformed case first. But of course, there are interesting questions also in the deformations. So this guy here, what is he? This D2, this D2. So the way that you construct it is this: you take you take a two cycle. So you take the twist operator that creates the two cycle. Actually, this is the Ramond sector of the CFT because fermions in the even cycle sectors, the fermions are periodic. So you have to take a specific state in the Clifford modules of the two cycle, and then you act with a left and the right supercharge, and you do this in a way that basically all the indices are contracted and this guy is neutral, and that's it, because that immediately has dimension 1 and is neutral under everything, and that's the guy. If I have to be super specific, because in the supercharges there was this index capital A, which was not something else, there are actually 4 such guys that you can consider. And the people typically consider is the singlet. So this A, some SU2 index, is an SU2 related to the SO4. If you take 3 as R4, there is an SO4. That's the 2 there. So the singlet under that SU2 is the guy that people consider. The other 3 are also moduli, which you can also study. It is an exactly marginal operator, yes. So this is as super symmetric as it can be, so everything is fine. For instance, there have been a lot of work, for instance, correlation functions of these symmetric orbifold type theories have been computed, and they are stable under these deformations. So there are all sorts of things that are known because this theory is so supersymmetric. It is a pretty beautiful theory. It is, yeah. I wish, I mean, there is a simple point, which is the potential limit of the D1, D5. So h equal to k equal to 0, h small, as opposed to k equal to 1 and h small. So that's some theory. And I don't know what theory it is. I would love to have a nice, it's some two-dimensional formal field theory with 4,4 supersymmetry. You would think that that narrows it down. But I cannot write what it is. I know what the spectrum is. It's be extremely interesting to find what it is and to compute other things than the spectrum, like 3-point functions and whatnot. And even to opt from the D1, D5 system by some analysis of the instant modular space and so on, it's never been done. So yeah, that's an important open challenge for people that are so inclined. I think it's that's really an important question, and not an easy one, but an important one. Well, the central charge, it depends how you count, because it is large n, so strictly speaking is infinity. But it's 6. I think it's 6 just because of supersymmetry. When you have n equal 4, the central charge tend to be integer. They're just too much SUSY. It's not like n equal 2.
Okay, so thank Alessandro for the first talk.
Yeah, so while if you can change the slide, I'll just remind I arrived later. I'll say some things about cost, and at the end of that, for reimbursed, I will show you how to do the reimbursement claim if you, okay? Because it's a system that maybe is not familiar to everybody, I can show it. But if you don't want, you'll get an email and you'll figure it out. I believe in you. You can do it. Okay, thank you very much. Okay, so yeah, just to say a few words about cost, and this is not only mandatory because cost is paying for, but it's possibly interesting and useful to you guys, because cost also gives you to organize other meetings, to get grants for young researchers and so on. So let me just tell you, first of all, what is cost? Well, cost is an association that promotes sciences, in particular in 41 member countries and 1 cooperator, which is Israel. So these are the colored countries. Out of the colored countries, 1 in green are called inclusive target countries. And basically, cost is particularly happy when activities are done that involve these countries. Some metric, they are more deserving of investment in order to further promote their science. As you see, cost is Europe, definitely Europe plus. So there are some countries that are certainly not in the European Union or in the Schengen, something else. Our action is one of the many cost actions. There are cost actions in physics, linguistics, economy, whatever. And it is about, well, what we all do, right? At the interface between theoretical physics and mathematics, advancing essentially the study of strongly coupled system, gravity, holography, and so on and so forth. There is a document which describes all these on the COST website. You're very welcome to read it. I doubt you will. It was our application, that not the document. This is more important. The action is articulated in 3 working groups: gauge theories, gravity and holography, and low-dimensional systems. And some activities are action activities. Some activities are working group activities, so they have a little bit more of a focus. For instance, this meeting is a slightly more focused meeting with respect to a general meeting of the action, okay? And when you join the action, you can just choose to participate. Maybe you just like low-dimensional systems, like we do here, but maybe you like all of them and you just participate in all of them, and that's absolutely fine. You can just indicate when you apply to join the action. There is a governing body, and these are representatives appointed by their own government, by something like the Science Foundation, which government appoints up to 2 people, and it makes decisions. And then there is a core group that the day-to-day running of the action. things that we do are meetings like these ones, schools. We support academic exchanges. If mailing list, you would have gotten emails about short-term scientific missions. These are travel grants for young researchers, especially, to spend a period of 1 to 4 weeks collaborating with somebody else in a coast country, from a coast country to typically. And then conference grants. These are grants for scientists that want to attend a conference not organized by us, but let's say they want to, well, strings. In this case, the dates didn't work out, but suppose that you have strings in Europe, and we could say, I want to go to strings. It's not organized by costs. To string math, string Fino, or whatever else, to give a presentation. Can you fund me to go to this conference? And people can apply for this purpose. So the way to get involved is, of course, just to come to the events. That's the best way. When there are events that you like, you can come. In some cases, you can get financial. Typically, this is for speakers or presenters of posters, especially for younger researchers. But sometimes there are fringe benefits. We cover things like the rental of the room or the social dinner or whatever. You can just propose new activities. So if you want to do it for the year, so from November of this year to October of the next year, this is the time. If you have some meeting in mind, you would like to organize a school, and reach out to either myself or some names that I will appear in a moment, or to some person that is the cost representative of your country, if you know who they are. They should have made themselves known. You can join the core group when we have calls for nominations. Sometimes we need a new person to help us with some particular aspect of running the action, so you can just volunteer. And if in your country the management committee does not have any member, or has only one member, you can volunteer to join the management committee. That is not done by us. You have to, I mean, you can write me, I can explain the complicated process in that case, but it goes through your board that has to appoint you. For the scientific activities, these are the people that you should get in touch with if you want to propose something, if you have something in mind. For each area, we have 2 leaders of each working group, and you can just shoot an email to, let's say, both of them. That's a simple saying, for next year, I would very much like to organize this activity in my university, and we have some money, and we want to do this. Does it fit with the action, etc., etc. There are other people, and each of us is in charge of a particular aspect. Sulkowski is the vice chair of the action and helps with the general running of things. Other coordinators are in charge of specific tasks in the action, like communication, ranting words. Well, you can all read. Or the people are in the room or were in the room and have run away to get on a flight. And the other thing is that cost action could be an incubator for other activities, like other collaborative networks, like doctoral networks, collaborative grants, or, and that's another thing to bear in mind, other cost actions. This cost action is already towards more than half of its second year, and it lasts 4 years. At some point, we already should start thinking about the fact that it will end and replace it, hopefully, because it's a good way to bring the community together and to have some funds for facilitate the interaction. So that's also something to bear in mind. And it doesn't need to be necessarily a cost action about all that we like as big as this one. You could say, well, maybe we should have a cost action on this particular subfield of research. If you think that you can sell it to the union as something that is worth financing, is certainly worth a try. And if you're interested in knowing how to do this, just come and talk to me. And I think almost the last thing that I wanted to say, apart from the fact that we have our general, which coincides with Eurostrings. These are the dates. You can find the link to the conference website. I didn't put it here because it's pretty long, but you can just register if you if you want to come, there is the possibility to apply for a contributor talk or a poster, in particular for younger students or younger researchers. So it would be very nice to see you all there. And that's it, I believe. The next thing will be about the reimbursement. I would really put everybody in free, set everybody free before. Okay, that's it. Questions on the course? Otherwise, you can just stick around and ask me or email. Don't be afraid. One last order of business. I would like, on behalf of all the speakers, to give a big thank you to all the organizers in this wonderful meeting and giving us the opportunity to be in Athens, beautiful city, which I've never seen, and talk about exciting science all together. Thank you very much.
Yeah, I would also like to take this opportunity to thank all of you, first of all, and for the very interesting and inspiring talks. I had a good time, this week, and if you're still staying, longer to enjoy, more. I would also like to thank COST of all supporting this, the organization of this meeting, and also the Theory Challenges Action, and especially Alessandro and Piona, that they played important role in the organization of this meeting. And I would also like to thank two graduate students that I think you all noticed around, chasing you for the signatures. So that's Elen Gogu and Adonis Stefas, that he's not here now. And I think that's it. I would also like to thank the University of Athens that some money towards the organization of this event. So thank you all again, and enjoy your stay. If you stay longer, have a good trip otherwise.
Okay, and now I will show this thing, but it's really just for the people that are reimbursed by COST and want to see it. I'll try to show how the reimbursement are done. And if people want to do it, I would suggest take out your laptop and you can just do it in real time if you want. Maybe I can do it here. Okay. Let's see. Let's see if the link works. Okay, then. No. We have to connect my laptop. Okay, yeah. Right. I was optimistic. You are there? Very good. I'll show you in a second. Yeah. So yeah, you should have gotten an email with this subject. Theory challenges or COST action 2211 invitation. Yeah, you can go ahead. Maybe I start turning on the other one to begin with.
If you just need the website, like a web browser.
No, I need a link, and somehow invitation link doesn't work.
Oh, okay.
It should be a clickable link, but no, okay. Can you click it?
I did.
Okay, then I don't need my computer.
Okay, good.
Very good. Is the one where you accepted, then if you click again that link, it should look exactly like this screen. And then Dan is complaining because I'm not logged into my account. Let me try to. Does it say also manage?
Reimbursement claim.
Reimbursement claim. That's where you have to go.
Update your choice.
On the left of update your choice should be reimbursement claim. Okay, so you can click on the cost just on this top left corner, and you will get to a login form and log in there. Right. You should also be able to see something like this, right? And now if you do reimbursement claim, you should have reimbursement claim. Yeah. So then we go to reimbursement claim. So you go to the costing, you log in, because if you are not logged in, it complains. And you go to reimbursement claim, and this is how it looks like, this reimbursement claim. And you think is when did you leave home, when did you arrive back home? So that's, well, that's what it's asking. It is important because the amount of money that you get is computed based on, and then you have to mark the days that you attend by clicking this. For instance, in my case, it's the last 2 days. One thing is that you signed the attendance sheet on the days that you attended. Somebody will be checking. It's a headache. Very good. So yeah, just to show, as I click this, it automatically computes the days based on departure, arrival, etc. Then, do you wish to claim the day? Are you a local participant? Do you want to wish 50%, or do you want to claim a lower daily allowance? So I suppose that when you were invited, you were told whether reimbursed some of it, all of it. So that's something that the organizer do, and you can put, for instance, lower amount and want 384 euros. I want 200 or whatever. Whatever was agreed, you put it here. Just okay. So people that have just a per diem, they can claim the whole per diem, which is automatically computed, so you don't need per amount. You still need to put, even if you are not the travel. So if you are claiming the travel, you put add long distance travel expense with your bus, train, whatever. It's only long distance means more than 100 kilometers. If you claim only the daily allowance, you still have to upload as supporting documents your boarding passes for, or whatever, train, if you took the train, I suppose most people flew, because we need a proof of when you departed and arrived to check that the computation is correct. No, because if you're not claiming the money, only the boarding passes. If you are claiming the money, ticket and boarding passes, if you're claiming the travel money. Exactly. So now you cannot click claim. You can save draft, and then tomorrow you should get an email, automated email from the same address that says you are now ready to submit your claim, and you can just reopen it and send the claim. I will send you, I think you already got it, but I will send you another file to attach and put in add supporting documents, and that's a form that our administration needs with like your signature and so on and so forth. That's is not a costing, but it's that we need to process. Basically, we need a signed document that's signed with us processing and reading your data and all these sort of lovely things. I think you got it. I will just ask. I send it again to Ioannis, and he will send it to everybody. You don't have to fish through your emails again to find the file, okay? And then tomorrow you can put everything together and send it. Okay. I think that's it. If you have questions on this stuff, ask me now, or otherwise we'll figure it out. Okay. If it's very simple, you can ask me. If it's something complicated, administrative, you will have to ask our secretary. Like if you had a strange itinerary and stuff like that. All right. Thanks.